In this video, we're going to introduce chapter 29, which is the sources of the magnetic field. So the picture that you see here is an example of the magnetic resonance imaging machine. It's called the MRI machine. So this uses very strong magnetic fields to examine a patient. So in this chapter, we're going to talk about how magnetic fields can be produced. So magnetic fields can be produced by currents. So this is a wire that carries a current. So a wire that carries a current is going to generate a magnetic field. And this equation here is called the Biot-Savart Law. It tells me how I can calculate the magnetic field. So if you remember, we said that an electric field can be produced from a charge. So if I know what the charge is, I can calculate the electric field at any point, where R is just the distance from the charge to the point where I'm interested in, and R hat is the unit vector. So I can calculate the magnetic field using this equation here. So again, my mu naught is just given by this value is 4 pi times 10 to the negative 7 Tesla meters per amps. Is just a constant. So I is the current in the wire. ds is a vector, is a length vector in the direction of the current. And r hat tells me is a unit vector between the S and the point where I'm calculating my magnetic field. And then r square, of course, is just the square of the distance between the source of the magnetic field and the point that I'm interested in doing my calculation. So again, we're going to be using this equation a lot, and you can see that the main difference between the electric field and the magnetic field is that electric fields can be produced from charges that are at rest as well as from charges that are in motion. In magnetic field, you can only produce magnetic field from charges that are moving. So a moving charge constitutes an electric current. So it means that if the current is equal to 0, if I is equal to 0, then there is no magnetic field. So this is really like the main difference between the electric field and the magnetic field. So electric field can be produced by charges at rest or maybe charges in motion. Then magnetic fields can only be produced by charges that are in motion. All right, so this is a quiz. So again, this is quiz number 29.1. It's a very interesting quiz. So you have a straight conductor here, a straight wire that carries the current I, and then all what it's going to ask you to do is to rank the points A, B, and C in terms of the magnitude of the magnetic field that is due to the current. So again, if you look at my ds vector here, so if my ds vector is pointing in the I direction, so at this point, you can say that point B is pointing in the J direction. Meanwhile, point C is pointing at some angle. So you can see that the distance from this point to this point is less than the distance from this point to this point. So it means that the magnetic field here at point B would be stronger than the magnetic field at point C. Now the magnetic field at point A is going to be 0 because at point A, the unit vector is going to be exactly in the same direction as my ds vector. So if you take the cross product of two vectors that are pointing in the same direction, you get a 0 contribution. So again, this is a quiz that I want you guys to take a look at, but if you analyze this very carefully, you're going to see that the magnetic field at point B would be greater than the magnetic field at point C, which is greater than the magnetic field at point A. All right, so basically, if you have a straight conductor, so this is a straight wire that carries a current, so we can use the right-hand rule to tell me what the direction of the magnetic field is going to be. So you have a wire that carries a current, so your thumb tells me my direction of the current, and then if you just curl your fingers around the wire, it tells you what the direction of the magnetic field is. So you can see that if I pick 2 points, so if I pick a point here, then the magnetic field at this point will be coming out. Meanwhile, at the point here is going in. So again, we need to know the difference right here. So the magnetic field lines are pointing like that. These are like circles, and this will be the direction of the current. So the right-hand rule can tell me the direction of the magnetic field. All right. So now we're going to look at our first example here. So this is example number 29.1, and we want to calculate the magnetic field from a thin wire, straight conductor. So again, I'm going to assume that the conductor has a length of L and it carries a current I. So I want to calculate the magnitude and direction of the magnetic field at a point P that is above the center of the wire due to this current. So again, just as we did for electric fields, you can set up your system right here. So this is the point P. The distance from here to here is A. This is my ds vector. So my ds vector is just pointing in the x direction here. My r hat is the vector from this point to that point, and this angle right here is just my theta. So I can set up everything in terms of vectors here. So I write my ds vector is just the x and the I hat. My unit vector r hat that is pointing from this point to this point here, I can write that unit vector as sine of theta in the I direction plus cosine of theta in the j direction. Because if this is my theta right here, then I can write this unit vector here as sine of theta in the I direction plus cosine of theta in the j direction. Now, if I take the cross product between my ds vector and my r hat vector, I simply get cosine of theta dx pointing in the k direction. So if I substitute this into my equation here, I know that this is I can calculate the magnetic field by doing this integral here. So if I substitute everything, I get this integral here. Then we need to substitute, just as we did for electric fields, we need to substitute cosine of theta here. So I can go ahead and write my r is just equals to the square root of x squared plus a squared. And then I know that cosine of theta is just equals to a over r, which is given by this. So if you substitute here and you do this integral, so this is an integral that we can look up this value on the table. But when we do this integral, we obtain this value here. So we can see that at this point P, the magnetic field is pointing out of the paper, which makes sense because we can, if you use the right-hand rule, so if the current is pointing in the I direction, if you just rub your fingers around the current, you're going to notice that your fingers will be pointing out. So the magnetic field at that point should be pointing out of the paper. All right, so now if we go into this expression that we've just calculated here, and then, so suppose that we're interested in looking at the magnetic field produced by an infinitely long straight wire. So we're saying that the length of the wire is way greater than the point A. Then under this approximation here, I can say that L over A squared. So if L is way larger than A, then all of this is just going to converge to 2. And so if I substitute 2 for all of this value right here, then you get the magnetic field of an infinitely long straight wire is just given by this equation right here. So again, the magnetic field is just mu naught times the current divided by 2 pi times A, where A is the distance from the center of the wire to the point P. And the magnetic field at that point P will be pointing in the k hat direction. So it means that it's coming out of the paper. All right, so let's look at this second example here. So in example number 29.2, we're going to look at the magnetic field due to a curved wire segment. So in this example here, we want to calculate the magnetic field at this point right here. So this is the point O. So the wire consists of two straight portions. So you have two portions. So this is a straight portion right here, and then this is also straight, and then this is the curve portion of the wire. So it means that current is going to come in this direction here, and then part of the current goes like that, and then exits in this direction here. So if I want to calculate the magnetic field, I can look at all the contributions that come from segment number A prime. So I can look at the segment from A prime to A, and then A to C, and C to C prime. Now I notice that when I set up my integrals, because the segment from A to A prime is always going to be, so if I set up my integrals here, then if I'm looking at the segment from A to A prime, then it means that my unit vector is going to be pointing in the same direction as my ds vector. So it means that if my unit vector is pointing in the same direction as my ds vector, then the cross product would give me 0. So it means that the contribution from A to A prime is 0, and the contribution from C to C prime is 0. So I only need to focus on this contribution that comes from the segment that goes from point A to C. Now, when I look at the segment that goes from point A to C, I notice that my r hat vector is always at 90 degrees with respect to my ds vector. So when I take the cross product of r hat and my ds, I simply get, because the angle is 90 degrees, I get a vector that is pointing at 90 degrees with respect to this point. But when I do the integral here, because that sine is equal to 90 degrees, I just get, if I calculate the magnitude, I can use this equation right here. So it's mu naught I over 4 pi. So the distance from this point to this point is r, which is a. So you have a squared, and then you have I ds. So when you do that integral, you just do the integral over ds. So the integral over ds is just the arc length, and the arc length is the distance from here to here, which is just the radius times the angle. So you get mu naught I over 4 pi a times the angle theta. Now what if, so what if I want to calculate the magnetic field at the center of a circular loop of radius r that carries a current I? So for a circular loop, we can just, so because we've already calculated this value here, and we said that for an arc, this is mu naught I over 4 pi a times the theta. Now, if you have a complete circle, you can just go in and substitute your theta is equals to 2 pi. And so you get mu naught times I divided by 2 times a, where a is just the radius. So this is the magnitude of the magnetic field produced by a circular loop of radius a. So this will be the magnetic field at the center. So notice that this is just the magnitude of the magnetic field. If you calculate what if you calculate the direction of the magnetic field, then in this case, for example, if the current is going in the clockwise direction, if the current is going in the clockwise direction, it means that the magnetic field will be pointing into the paper.